I'd like to finish off by introducing this concept called the regular representations. So regular representations are kind of the most natural way of representing a group inside some B of H. Okay, so the reason is that they're really natural and they're really nice, and that's why a lot of times this is kind of the object of study when you talk about representations of a group. And in operator algebra, these regular representations also generate a bunch of really nice and important operator algebra. For example, if you taken any higher level operator algebra, for example, every group is associated with a reduced and the full group C star algebra. The reduced one is essentially generated by these left regular representations. And if you go to the Van Neumann algebra, the Van Neumann algebra of a group is also kind of related to these kind of representation. You take the weak operator closure of them, all right? So that's why they're important. So let me give you the definition. So they're really simple. So the idea is that if you consider the following, so if you consider pi L, so that's the left representation. So if you represent it using on the L2 of G, so L2 of G is going to be a Hilbert space. It's basically all the L2 functions. And what you can do is that because your integral on G is going to be left translation invariant, so if you just let x to be mapped to the left translation, so here the Lx, you take an L2 function, and if you evaluate y, that's just equals to f of x inverse y, all right? Because of left invariant translation, then this pi L is going to be unitary, okay? So this is quite clear. So for each this Lx is inside the unitary of the L2 of G. That's just because of the dx, the Haar measure is left invariant. All right. So because of that, now you have some Lx inside the unitary, and if you translate it by Lx and by Ly again, then it's the L of xy. And then if you want to do the adjoint, so if you do the Lx adjoint, so let's just say Lx star of f. Okay, so what it does is essentially, if you look at the integral to g, that's essentially equals to the f with you move the adjoint to the other side. That's how define the translation. So this one is equals to, so let's write it out. So this is essentially equals to f of x, I should say y, and then you evaluate the Lxg, evaluate y, and then you take the conjugate dy, all right? So this is equals to integral of the y, and then you have the g of the x inverse y, okay, and then the whole thing dy, and then you do the conjugate. All right, so now because of left translation invariant, now you can translate this y by x. So you move the replace y by xy, so you have f of xy, and then now you have a gy bar dy. So this one is going to be equal to the following. So this is essentially the same as you translate f by x inverse, because there's no longer inverse there, and you have g on the other side, okay? So because of that, you have this Lx star, the adjoint operator, is basically the left translation by the inverse. Okay, so basically this proves that you have a star homomorphism, and so this is called the left regular representations, and this is a unitary representation. And similarly, you can also ask, well, how about let's do the other side? So for the right hand side, it's slightly trickier. So let me just write it down like that. So for the right hand side, you can do the following. So you can also say pi r is from G to the unitaries on the L2 of G. But remember, because the whole reason this works is that we're integrating against the left Haar measure. And if you want to do the right, we need to do the L2 space, but with respect to the right Haar measure instead of the left. Okay, so this is a right Haar measure. So essentially, you do the same. You map x to the Rx. Okay, so that does work. Okay, so you do have a unitary representation this way, but that's most of the time you want to say, well, what's the relationship with with the right translation respect to the L2 space for the left, okay? Because, well, now you kind of change from the L2 space, your two L2 space are kind of different. So a lot of time we also do the other one. So let's do pi tilde r to be the following. So if I want to say pi tilde r of f, okay, so here f is inside the L2 of G. So here is the d mu, mu is the left invariant Haar measure. Then this one, let's evaluate this whole thing at y. Okay, this evaluation is given by the following. So I want to do the right translation by x. But if I want to keep my f in the L2 space of the left Haar measure, then I need to compensate it by the modular function. So I need to say delta of x actually to the half. All right, and so why this is actually a unitary, you can just integrate, for example, let's say integrate pi r tilde of x with f, and then let's do the pi r tilde of x of g conjugate. Okay, so you take the inner product of these two. So here is dy. So you evaluate at y for each of these functions, and what you have is that you integrate. So now you have the delta of x in the outside. And then you have the f of yx, and then you have a g of the yx, g bar of yx dy, all right? And so what you can do is that because your x is, well, now you're integrating against this dy, well, you can, using the modular function, you can reverse it to a y inverse, okay? But by doing that, you need to compensate by this modular function of y inverse. So this is equals to modular function homomorphism. So let me just write the y inverse inside here. And then you replace each of these y by the y inverse, okay? G of the y inverse x dy. And so now you can, what you can do is that, well, now we move the x, we put the inverse in there again. So this is the integral of the, so I say, well, this is equals to the x y inverse, okay? Or x inverse y inverse. And then you have the g of the x inverse y, the whole thing inverse, okay, dy. And then you have a delta of xy inverse. All right, and now you can do the left translation by x, okay? So you can translate all the y by, basically make all the x, all the y by xy. So this is the integral of the delta x, so here is xy inverse, and then you have the f of y inverse, and then you have a g of the y inverse dy. Okay, I missed the bar always. All right, so the good thing about the modular function is that it's a homomorphism, so it doesn't really matter which way we put the x inverse. So you end up with the delta y inverse, and you have f of y inverse, and you have a g of y inverse conjugate dy. This is now you put the inverse back, so this is integral of f g bar, okay? So basically show that the this pi tilde of r also preserves the inner product. So there is going to be a unitary representation as well, okay? Well, in general, when you look at the literature, you rarely see these right regular representation. Most of the time we always talk about the left regular representation. The reason is quite simple, is because they are actually unitary equivalent, okay? So here's the proposition. So this pi tilde of r, the right regular representation, and this left regular representation, they're actually unitary equivalent, okay? So in other words, usually we only look at the left, okay? So the proof is fairly simple, so I just need to find a unitary that implement this switch. So what you can do is you can define a L2 to L2. So here the L2 is respect to the left Haar measure. So what you do is you let f, and you map it to the f of x inverse, but then you multiply by the modular function of inverse to the half. All right. And it's really routine to check that U is a unitary. That's essentially just the formula for the modular function. So I'll leave that to you. So U is indeed a unitary. That's really simple. And if you look at so pi L composed with a U, and if you apply to some function, you can see that is basically U composed with pi R tilde of x. Okay, these two are really simple exercises. Just plug in the algebraic formula and you can check they have to be the same formula. Okay, so in other words, the right regular representation is always unitarily equivalent to the left. So that's why we usually only look at the left one.